Hello, welcome to the Raman Spectroscopy and its applications in bioprocessing webinar. My name is Yiğit. I'm a New England region-based applications engineer at ProAnalytics. ProAnalytics represents many well-known suppliers in process analytical technologies and single-use fields in many territories of the United States. Today, I'll be talking about the physics and chemistry behind Raman spectroscopy, comparison with other spectroscopy techniques, data processing steps, Raman spectroscopy upstream and downstream applications, the advantages of using Raman spectroscopy, and the advantages of using instruments from Tornado Spectral Systems that ProAnalytics represents for your Raman spectroscopy measurements. I hope this webinar will teach you the science behind the Raman spectroscopy, and it will demonstrate the great advantages of using Raman spectroscopy in your processes. If you haven't already integrated in your processes, I hope it will help with your decision on using Raman in your processes. You can type your questions in the chat bar, and I'll be answering them during the session, or after the session, or getting back to you in person after the session. All right. So let's start the webinar with explaining what optical spectroscopy is and the physics behind Raman spectroscopy. First of all, optical spectroscopy is a subset of spectroscopy and is often employed as an analysis technique to measure the interactions of different wavelengths of light with matter to determine the physical and chemical properties of the sample with which the light is interacted. Hence, it provides a unique fingerprint for different atomic, molecular, and crystal structures in a sample. Variations in the atomic and molecular structures result in different spectroscopic fingerprints, and optical spectroscopy can be used to identify and quantify these structures. Optical spectroscopy in itself can be divided into several branches as well, but the most employed classes in the bioprocessing field are absorption spectroscopy, luminescence spectroscopy, and Raman spectroscopy. So let's start with absorption spectroscopy. The most common method of absorption spectroscopy is near-infrared spectroscopy. The absorbance of incident light in the near-infrared region of the spectrum, which consists wavelengths from 780 nanometers to 2500 nanometers, differs from molecule to molecule, which yields a unique spectrum within the NIR region of the light due to Beer-Lambert law that relates the attenuation of light to the absorptivity and concentration of the sample through which the light is traveling. Near-infrared spectroscopy measures combinations and overtones of molecular vibrations generated due to the change in the dipole moment of a molecule with covalent hydrogen bonds, such as CH, OH, and NH bonds. The changes in the dipole moment of covalent hydrogen bonds result in broad and overlap bands, as typically there are multiples of these bonds. NIR spectroscopy has advantages such as cheaper NIRS measurement equipment, the ability to measure absorption through thick container walls thanks to the longer path length, and much higher signal level for the same number of photons, resulting in lower exposure times. But NIRS has a major drawback for bioprocessing. It does not generate the same level of molecular specificity compared to Raman spectroscopy, which we'll discuss throughout the webinar. Another common method of absorption spectroscopy is UV-Vis spectroscopy. UV-Vis spectroscopy utilizes the ultraviolet and visible ranges of the light spectrum, which typically consists of 200 nanometers to 800 nanometers range of the spectrum. The molecule of concern changes electronic energy states due to the absorption of light within the UV-Vis range of the spectrum. For the absorption to happen, the energy of the incident light must match the energy of a possible transition between electronic states of the molecule. The transition happens from a lower energy state to a higher energy state, called the excited state. Since different bonds have different energy states, the absorption occurs at different wavelengths of light for different molecules, resulting in different absorbance curves. The degree of absorption is also critical to determine the concentration of the sample, hence the quantification of the sample. Next, let's talk about the luminescence spectroscopy. The most common method of luminescence spectroscopy is fluorescence spectroscopy, where the fluorophore is excited to a higher energy state by an incident photon and then emits light at a different wavelength than the incident wavelength by dropping to a lower energy state. Different fluorophores have different emission spectra, and this method can collect information on fluorescent compounds in the sample. UV spectroscopy and fluorescence spectroscopy are complementary methods, as fluorescence spectroscopy measures transitions from higher electronic energy states to the ground electronic energy state, whereas UV spectroscopy measures transitions from lower electronic energy states to higher electronic energy states. The third optical spectroscopy type that is very commonly used is scattering spectroscopy. Throughout the webinar, we'll be focusing on Raman spectroscopy and its applications in bioprocessing and its advantages. Raman spectroscopy is a subset of scattering spectroscopy. Raman, on the other hand, measures the vibrational frequency or energy of molecules when they are hit with a laser. This resembles a tuning fork for molecules. The laser is the tuning fork, and then when it touches a molecule, it will make that molecule vibrate or hum. And each molecule has its own vibrational profile, like a fingerprint. Many of these molecular fingerprints can be found in peer-reviewed papers and publications, or just by searching on the web. This is very similar to how mass spec was done back in the day before it was very widely accepted. Many scientists publish papers on mass spec profiles, and Raman is very similar. A photon of light supplied by the laser shoots a photon into the sample where it is absorbed temporarily, the tuning fork touching the molecule. The laser intensity is plotted on the y-axis, and the molecular energy states are plotted on the x-axis as V. V is the vibrational energy state, and molecules can have multiple energy states. Vs is the scattering, and Vi is the incidental, which is always a fixed path in the instrument. The incidental refers to the angle that the laser or the photon was shot into the sample. If the intensity of the photon hitting the sample is equal to the amount of light scattered, this is called Rayleigh scattering. The elastic scattering of the photons or the Rayleigh scattering accounts for the majority of the scattering. This state can be thought of as the tuning fork touching the sample, and it mirrors back at the same energy. So let's talk about the three scattering profiles of Raman and the basics on how Raman spectroscopy works. There are three things that can happen in Raman. The first one that we already described is Rayleigh scattering. This is when the energy is reflected back to the instrument at the same intensity as it went to the sample. Therefore, Vs equals Vi. Raman spectroscopy, on the other hand, measures the tiny proportion of the photons that are scattered inelastically. The vibrational state of a molecule can be excited to an energy level above the ground state by a photon that loses energy during the Stokes scattering event. The second thing that can happen is when the photon hits the sample and we move the vibrational energy state from V0 to V1. So we have touched the tuning fork to the molecule, and now it is vibrating at a slightly higher energy state from the original ground state. So this is called the Stokes line, where the amount of measured vibrational energy is less than the amount of energy that went into the sample. So Vs is less than Vi. And the third profile is the anti-Stokes line. In this case, the sample is already in an excited state. For example, the sample could be heated and the molecules are already in an excited state. But this time the light is scattered with more intensity once the sample has reached the ground state. In this case, Vs is greater than Vi. The photon that scatters can gain energy from the drop of the vibrational state of the molecule, which is called anti-Stokes line. These two scattering events are the core of Raman spectroscopy, but typically Stokes scattering is used. Rayleigh and anti-Stokes lines are filtered out. For Raman spectroscopy using Stokes line, the light source and the detectors have to be very sensitive. Raman spectroscopy has been gaining popularity due to the improvements around the technology. The detectors and the energy sources have dramatically improved over the years, making Raman an extremely useful analysis tool. The most major optical spectroscopy type that is compared to Raman spectroscopy is near-infrared spectroscopy. Raman spectroscopy is a complementary method to NIRS as it measures a different molecule of the different spectrum of the molecule. NIRS measures the change in dipole moment during molecular vibrations causing absorption, whereas Raman spectroscopy measures the change in polarizability during the molecular motions. This makes Raman spectroscopy inherently advantageous to measure analytes and metabolites in aqueous solutions and environment, as the inelastic scattering spectrum of polar molecules are less efficient than the nonpolar ones. And the Raman spectrum of water is weaker compared to NIR absorption of water. The weakness of Raman spectrum of polar molecules results in less interference from polar molecules such as water in the band of concern and facilitates the bioprocess monitoring, cell culture media, and protein analysis. Before we talk about the applications of Raman in bioprocessing and process analytical technologies, let's shortly talk about the data processing steps that Raman requires. Raman spectroscopy typically requires multivariate data analysis to be able to work within the intended application. Various denoising and smoothing filters, baseline and background correction, spike and scatter corrections, including fluorescence collection and cosmic ray removal, wave number and intensity corrections, and normalization and dimension reduction methods are used to pre-process the experimental Raman spectra data. Then the calibration and validation sets are created from the experimental data. Root mean square error on the calibration data and root mean square error on the prediction data are important parameters to check the validity of the model that is built. Minimizing these errors with the created model is the goal. Partial least squares, principal component analysis, artificial neural networks, and net analyte signal algorithms are commonly employed for the predictions. Model is optimized and pre-processing is cross-validated through the validation dataset, and at the end, spectra are predicted from the unknown data. And last of all, before moving on to the Raman spectroscopy applications in bioprocessing, I would like to take a step back and I would like to talk about types of process analytical technologies. The ability to monitor and control a bioreactor environment is of critical importance to ensure minimal or no deviation from the upstream process strategy, as deviations could lead to changes in the properties of the molecule. There are 4 classes of measurements to achieve this objective: inline, online, atline, and offline. Accurate inline and online measurements provide real-time or near real-time data. By comparing the targets or the set points to the instantaneous measurement data provided by accurate inline and online measurements, one can take corrective measures to eliminate deviations from the control strategies. Both atline and offline measurements require sample removal from the reactor to measure parameters by a distant analyzer. Atline measurements refer to the measurements done by analyzers that are close to the reactor, getting measurement data in minutes to hours. Offline measurements result in even longer delays in the processing of the sample. Therefore, in-process control strategies can only be enabled by inline or online measurements. The final goal of the PAT is to integrate different aspects of bioprocessing, such as chemical, physical, mathematical, and biological analysis. Spectroscopic methods are one of the most employed PAT tools, and Raman spectroscopy with the relevant mathematical models is one of the most prominent measurement techniques in monitoring bacterial, yeast, and mammalian culture systems. And some of the important parameters to measure are cell viability, viable cell density, glucose, amino acid, and product concentration. Raman spectroscopy is one of the biggest PAT tools in the upstream and downstream bioprocessing. I will first talk about the upstream applications. Raman spectroscopy has shown accurate measurements and predictions of glucose, lactate, viable cell density, and product concentration, leading to adaptive or closed-loop control strategies, such as maintaining glucose concentration at a fixed set point or to minimize lactate accumulation by adjusting the glucose feed rate. It is also demonstrated that Raman spectroscopy can monitor monoclonal antibodies in real time and distinguish between glycosylated and non-glycosylated molecules. Raman spectroscopy is also shown to have good correlation with traditional offline and atline metabolite analyzers. In one study seen on the left, glucose measurements from MAB-expressing cell line culture by Raman spectrum demonstrated good correlation with reference data from Flex2 analyzer from Nova Biomedical. Raman spectroscopy spectrum-based predictive models for glucose controlling the cell culture displayed equivalent glucose and viable cell count profiles compared to the reference data. In another study on the right, predictions of total and viable cell densities and the viability from Raman spectra track the CDEX cell counter measurements done offline. Other studies show good correlation with HPLC, UV-Vis spectroscopy analyzers, and various chemistry analyzers. The detailed chemical information that is obtained by Raman spectrum thanks to its sharper bands enables further ability of transferring models from small-scale R&D settings to large-scale manufacturing settings. After talking about studies from the literature, let's talk about a study from Tornado Spectral Systems. Here is a typical profile from Tornado Spectral Systems. The data you are looking at is the data from 25 bioreactors running in parallel. These are all mammalian runs, CHO cells. You can see that the runs are very consistent. In fact, since Raman captures everything, you can look at several metabolite profiles at once. Let's look at glucose in these bioreactors. We know that Raman profile of glucose in our media can be found in the frequency or Raman shift area of 1041 or 1067 wave number, and at 1085 and 1153 wave number. You can see the two bands with the original orange within the orange rectangles on the graphic. Looking at the data over several days, you can see the glucose levels decrease and increase, hence the sawtooth curve of the sawtooth design of the curve. You are looking at pumps turning on over the run with sharp spikes of glucose additions. Some people refer to these events as a bolus feeds. You can see that the accuracy is very good, plus minus 0.3 grams per liter with an R2 value of 0.98. Through this, you can tie your glucose measurements into your control loops. You can multiplex with multiple metabolites, and you can QC the media and buffer at the same time. So remember how I mentioned Raman captures everything in your run? let's look at the lactate profiles of these runs. We know that lactate is in 830 to 879 Wave number. The first graph shows lactate building up over time, which is what you expect because lactate is one of the metabolites of glucose, hence no sawtooth design. The red line is the lactate being produced by the cells after they consume the glucose. The accuracy is excellent, plus minus 0.2 grams per liter of lactate. And now let's just overlay the data from the previous slides. And it is what you expect during a normal fed batch process. Glucose goes down and lactate goes up. The reason for the sawtooth design of glucose is an addition to the reactor by a feed pump. You're adding glucose, but lactate is the final metabolite, produced or secreted by the cells after they consume the glucose. Therefore, you can multiplex several metabolite profiles at once since Tornado Raman captures everything. You can go back and do the glutamine and glutamate profiles and tie everything into your control loops. The idea that one instrument has so much versatility in the lab is very rare. You can test your API, your media chemistry, buffer chemistry, metabolite profiles all with one instrument. At the end, you get the versatility of this instrument that gives data like a mass spec without the prep and in real time. If you pair Raman with a biocapacitance probe from Aber, you can have the full QC built into your process by the addition of viability on top. To summarize the upstream applications, Raman spectroscopy, along with the appropriate mathematical modeling for multivariate data analysis, is demonstrated in numerous papers to be able to measure and predict existence or concentration of amino acids like glutamine and glycine, DNA and RNA bases, fatty acids and fats, hormones, organic acids like lactate, salts, sugars like glucose, and other compounds, and quantify key process parameters such as total cell density, viable cell density, product titer, viability, antibody titer, and osmolality. Raman spectroscopy is used in microbial fermentation systems and cell culture systems using, for example, CHO cells. Let's move on to the downstream applications of Raman spectroscopy as we wrapped up the upstream applications of Raman spectroscopy. But let's first talk about PAT in downstream applications. Monitoring the critical process parameters with various sensors is the main application of PAT in downstream processes. The measurement results are analyzed by univariate analysis and operator knowledge. However, this is typically not enough to have an understanding on the critical quality attributes of the product. CQAs include product multimers and product charge variants, host cell impurities such as host cell proteins, DNA and lipids, and resin leachables. These are typically monitored by atline and online analysis. Various HPLC techniques are used to monitor high and low molecular weight species content, charge and glycosylation variants and aggregates, and they are typically employed as atline analytical techniques in downstream processes. The typical monitoring technique for host-related impurities is immunological assays. All these techniques require long analysis times, and even though there has been progress to adapt them into real-time control strategies, the long analysis times are still a bottleneck for real-time monitoring and real-time process control. Flow sensors and flow meters, pressure sensors, pH and conductivity probes, and spectroscopic sensors are some examples of PAT tools to achieve real-time monitoring and process control. Spectroscopic techniques, especially, are great PAT tools to accomplish these goals, and Raman is one of the most powerful spectroscopic techniques that has a great potential for future applications. Raman spectroscopy is already employed in downstream processing applications such as measurement of product concentration and product aggregation. The product concentration estimation and monitoring of monoclonal antibodies is critical in continuous perfusion processes. This part can be accomplished by UV-vis spectroscopy without the need for advanced predictive mathematical modeling that Raman spectroscopy requires. However, Raman spectroscopy achieves one goal that UV spectroscopy cannot achieve. Raman spectroscopy with quantitative modeling can be used for aggregate analysis. High concentrations of aggregate map types in the samples can be differentiated from each other due to having different Raman spectra. Glycosylation. This entails distinguishing glycosylated and non-glycosylated proteins. And lastly, membrane fouling. The fouling of immersion probes within cross-flow filtration units can be monitored as well. Even though this could be challenging due to complex background and weak signal of proteins, there are promising signs. One paper here on the right shows good correlation between Raman predictions of map concentration versus measurements with UPLC. The downstream processing applications of Raman spectroscopy are still a very active research field, and more will be evaluated and employed within the near future, as Raman spectroscopy will be an established analytical method within downstream processing field. So now let's talk about an application note from Tornado Spectral Systems. So, we'll present data from two proteins that are exactly alike, except that RNase B has a sugar embedded in the protein. This shows the sensitivity of Tornado instrument, the ability to distinguish two isomeric forms within a single glycosylation site. So here is the Raman profile of RNase A, and here is the Raman profile of RNase B. Overlaying on top of each other, the first orange circle shows the missing glycosylation or sugar about 1350 wave number in the Raman spectrum. You can see that RNase B has the sugar and RNase A does not. The second orange circle is where there is a turn or bend in the protein between RNase A and RNase B. Unlike the upstream one, these are purified samples, so the solution is more binary, just the proteins in the same buffer. It's not like the metabolite analysis where you are capturing multiple Raman profiles of everything in the soup. And the limits of detection is about 120 parts per meter in this study. So throughout this presentation, many use cases and advantages of using Raman spectroscopy are mentioned. To summarize them before ending the presentation with product offerings from Tornado Spectral Systems, here are some advantages of integrating Raman spectroscopy in your process control. Raman spectroscopy instrumentation is very easy to integrate on different setups, and with options such as immersion probes in bioreactors, vessels, and slipstreams, as well as large volumetric probes in manufacturing systems and non-contact probes for non-contact detection. Fiber optic cabling and multiplexing enables flexible installations. Raman spectroscopy has an inherent advantage of being able to measure analytes in aqueous solutions due to the diminished interference from water, resulting in more accurate measurements than the other online and inline spectroscopic and non-spectroscopic analysis techniques. It has high chemical specificity to key process parameters, and it is very versatile to many applications. It enables both qualitative and quantitative analysis. It enables easy tech transfer, and it is scalable from lab to pilot to manufacturing. Since Raman spectroscopy is a non-invasive measurement, it reduces the contamination risks and enables remote monitoring of the process. Inline and online measurements enable process control and corrections from the deviations in real time, therefore increasing the process robustness. Raman spectroscopy enables the ability to monitor product quality continuously in real time and the development of predictive and advanced feedback control strategies and upstream process optimization. It enables the scalability of prediction models and methods from mini bioreactors to large-scale production bioreactors. This results in higher process efficiency and product concentration, better and more consistent product quality, shorter cycle times, and lower costs due to the reduced need for calibration efforts for different volumes of bioreactors. And many Raman instruments are compatible with various automation platforms. So lastly, let's talk about the Raman spectroscopy instruments. Some companies will use unfiltered lasers in their instruments. You can think of this as more of a shotgun effect, where the light is just scattered over the sample and the instrument detects the resulting Raman scatter. Open beam path results in high energy throughput as there's no blockage, but poor resolution. Some companies, on the other hand, will try to focus their beam onto the sample by using slits. The issue is that it blocks 75 to 95% of the light energy, so the detection gives a low signal, but you get okay or decent resolution. Adding a slit results in good resolution, but most of the light is blocked. Therefore, the energy throughput is significantly reduced. But if you are looking at two compounds that are close, it is difficult to distinguish their profiles from each other. Tornado has created HTVS technology, or high throughput virtual slits, which anamorphically reshapes the beam so that 95% of the energy hits the sample. This results in up to 10% faster measurements, better process responsivity, 3 times better measurement quality, better sensitivity for lower detection limits, and good quality and fast measurements with low laser power. With tornado detectors, you get excellent throughput and resolution when compared to other Raman spectrometers. HTVS technology is proprietary to tornado spectral systems. And lastly, since there are no moving parts, the durability, stability, longevity, calibration, stability, and transferability are much better. Now let's talk about the Raman analyzer options from Tornado. You see the two main options on the screen. Both of them have 785 nanometer laser light source with adjustable power between 20 to 495 milliwatts. Both of them provide fast measurements under 30 seconds with high sensitivity and resolution at low detection limits. And both of them pairs directly with immersion probes or non-contact probes. Now let's talk about the differences. HyperFlux Pro Plus works with a laptop or desktop with the SpectralSoft software, whereas Process Guardian on the right works as a standalone device with a built-in computer. So let's talk about the probes now. The non-contact probe pairs nicely with the analysis of powder beds and analysis of raw materials, salts, media components, etc. The contact probe works with stainless steels or single-use bioreactors. There are also some other probes from third-party companies that can be used with Tornado spectrometers, such as one from Blaze. The single-use bioreactors would use a thermoprobe bellow to insert the probe into the reactor via an aseptic connector. And lastly, we have the SpectroPort Raman probe. Spectroport Raman probe pairs with the Amber system. It plugs directly into the analysis module and is used to view metabolite profiles. This shows how accepted Raman is in the industry. The sensitivity and the speed of the instrument gives results very quickly. And you can always go back and reanalyze data for other metabolite profiles. So now we'll summarize the product offering from Tornado. First of all, you'll need to choose your analyzer. It can be the Hyperflux Flow Plus, the Superflux, or the Process Guardian. Second of all, get the multiplexer if you need one. Thirdly, choose your probes. So it can be the Hudson 785 non-contact, Hudson 785 immersion, or the Spectroport. If you need it, use it with the SpectralSoft software. And there are also a lot more accessories, custom designs, and integrated solutions. For all of these, please feel free to contact ProAnalytics. Before wrapping up my webinar, I would like to introduce ProAnalytics. Here's a list of suppliers that we represent. Our team members are all experts in bioprocessing, and we provide various solutions for your needs. As can be seen on the slide, we represent numerous suppliers and distribute numerous products. Today we focused on the Raman Spectroscopy technology and Tornado products from Tornado Spectral Systems, but as you can see, we distribute various products such as biocapacitance-based variable cell density monitors or optical-based total cell density monitors from Aber Instruments, all the sampling solutions and process information management systems from SecureCell, off-gas monitors from BlueSense, online metabolite analyzers from Trace Analytics, and so on. We, as ProAnalytics, also provide numerous on-site and remote services as you can see on the slide. Please feel free to contact us for your service needs, as we could help you with improving your processes from small-scale R&D to large-scale manufacturing, from upstream to downstream. This concludes my presentation. Thank you so much for listening to Raman Spectroscopy in Bioprocessing webinar. I'll be answering your questions now. And in the meantime, please feel free to visit our website for more information on Raman Spectroscopy product offerings and other technologies. Feel free to email us, and please feel free to email me for further questions and personal contact. Thank you so much, and I'll be answering your questions right now.